Howdy, everybody. Here for day 23 of Advent of Code. Let me just say before we get started, thank you. I've really enjoyed reading your comments and the ideas you had about like your solutions to problems. Um, the holidays are clearly getting busy, so I'm going to try and make this video relatively short. I am going to have like a quick interlude into graph theory at the beginning here. So if you want to skip to the actual solutions, I've been trying to do like the sections or chapters or whatever they call them. So um, feel free to skip ahead. But otherwise, again, thank you very much for all your comments and thoughts and watching the videos. And as we're coming to an end here, hopefully we'll be able to do some other things. Particularly this one, again, I don't have a ton of time, so I'm going to try and go through it very quickly. But sorry, I'm just going to get my pad here. Once we're done with this, maybe I can go into a little bit further. And we can go into the details of this one a little bit further. But with that, let's get started. So first, just talking about the problem. For part one, you've got things working, but it's taking time for the water to be like to turn into snow, and so you've got some time to take a walk, and so you've got another grid. A lot of grids this year, right? What are the key things to look at in the grid? First of all is where it is any place that's a dot is a place that you can go. Any place that's a hash is a place you can't. They call it a forest. And then you have these slopes here, right? And these slopes give directionality to where you can hike. And the idea is they're slippery. So if you step on one of them, you have to go in that direction. And what is that saying is you can't go backwards, right? So if somehow you found yourself going up this path and you were right here, you can't go up this thing. You know you're stuck. So that's not like a valid path to the end, right? The end is down here. Your goal is to start here and to get down here, but they want you to do it in the longest path, right? They're asking, what is the longest path from here to here? And think about there's like a secret to that when you hear longest path, and we'll talk about that. But if you're familiar with graph theory or just solving problems like this before, longest path problems have been researched a lot, so we know a lot about them, right? But stepping back to the problem itself, what they're asking is, hey, if I'm traversing this path, what's the longest way I could go, right? And they give this solution right here. Here's the longest path from the beginning to the end, right? You could go down this way and traverse here, but it would take you like fewer steps to get there, right? And so the question is which one takes the most steps or the longest path? And you can see I have this up here already, the longest path problem. That's what we want to talk about, right? Is like the problem itself, there's not much to it, is you think of your traversing, but do you know the secret? And what is the secret of the longest path problems? In general, they are NP hard. And what does that mean? That's just a fancy way of saying there's not an efficient solution for it. What it does say, though, is this P part is down here is key for part one, is it says if the solution is a directed acyclic graph, then there is a linear time solution for it. Meaning, like, it's not like it's not as fast as Dijkstra's, but it is fast in that you can like given a number of nodes and edges, you'll only have to do them once, and I'll show you what that means. But the idea is there's a somewhat efficient solution for a directed acyclical graph. But for just a general graph, it's known to be NP hard, meaning there's nothing you can do but just brute force it, essentially, is the way to think about it. And that's the key to this problem. So when you get a problem like this, you should start looking for like graph theory solutions. What is the graph theory thing? And so this one, just because I've done some stuff with graphs before, I was familiar with this. And so I immediately, the alarm bells are going off. So you have to ask yourself, like, what is it that I need to do to like solve this problem? And is the problem directed acyclic where I can solve it relatively efficiency, or is it like NP hard, meaning I'm just going to have to try all possible versions of the path, right? And so I really briefly, I just want to talk about how I know, like, at least when I was initially doing this years ago, an initial thought may have been, oh, well, isn't this just like kind of the opposite of Dijkstra? Like, instead of the smallest, can I find the largest? And the reason that doesn't work is just the way that pathing works, right? If you think about what Dijkstra is trying to do, the algorithm, the reason it's efficient and you can do it faster than just like checking all the nodes is you're just kind of tracking like the minimum distances along the frontier, right? So think about Dijkstra's algorithm is you start here and you consider all the nodes, right? So this one has a weight of 2, this one has a weight of 7. You put those on your to-do list, and then you pick the minimum one of them, right? And in this case, it's 2, so you go down 2, and now you're going to visit these ones. And so now you have a distance of 22 and 13. But this one is shorter, right? And so you say, okay, I'm going to actually do this path first. And it only has 1, which is 4. And so now you have a path of 11, a path of 22, and a path of 13. You pick the smallest one, and that gets you here, right? And you've eliminated checking this path, right? You haven't gone down this one or down this one to find the shortest. You found it going this way. That's what makes Dijkstra's efficient, is that, like, because it's the shortest path, and you're only visiting those shortest distances, eventually when you get here, you have reached the shortest path and you've eliminated, some subset of the graph that you haven't had to check. So if you're thinking to yourself, can I use the negative solution? The answer to it is actually no, you can't. And why can't you do that? Consider like, I think this one doesn't quite work. Let's put a 2 right up here. So consider like this graph right here where this is 27. If you can't do a negative weight on this, Dijkstra's won't work. And why is that? Right, if you're considering these 2 paths right here, you'll start here and that's 2, and this is 27. And then you're gonna add these 2 from this one, right? So you're gonna get 13 to here, 22 to here, and 27 to here. Dijkstra's would then consider this path now as 13, and then this path is 18 to find the solution, right? Because these ones are all shorter than these ones. But that is not the actual correct path. You can kind of visually see it is going this way, only costs 2. So Dijkstra's doesn't actually work with negative weights, or you can't think of it as like the inverse. You can't do like the inverse of Dijkstra to get the longest path. And so that's just like a brief reason, like, hey, why is this an actual hard problem to solve? And it's for that reason. You literally have to just like try all the cases. And it turns out in an acyclic graph, directed acyclic graph, which is like what this is, the way that you efficiently solve it, maybe go back to this one, is just trying all the places, right? And because it's acyclic, it's always going in one direction. You can kind of keep track as you go, right? So think about like the way to think about it is I'm going to go here, and I know it's 7 to here, and then 4 to here. That hits the end. And I'm going to go back up, and I'm going to go here. That's 26, and I'm going to go here. That's 18. So I know 26 is the largest, and so this is the largest path. And that's kind of because it's a directed acyclic graph, you can solve it in like linear time, essentially saying, I just need to kind of traverse all the paths down, and that will get me to my solution. Where it becomes NP hard is if there isn't the directionality. So let's just ignore the arrows for a second, right? And we'll have to add a graph point here to like have it make sense. Like, let's say that it's this one right here, and it's a 20. Again, ignore all the arrows. because we're no longer acyclic, right? How do you do the path finding here? Well, you can't do the same thing, right? There's no directionality, so you can actually go here, and then check here. Obviously, you can't go this way because you've already been there, so that doesn't count. We aren't like backtracking is the way to think about it. There's never backtracking. But you can potentially, like the longest solution could be to go here, then back up here, and then back up here, and then down here. And it turns out, like, if you actually draw that, that is the case, right? But you have to check all those, right? Because whenever you're right here, obviously you can check right here, and that will give you a distance to the end. But you have to also consider, is it further to, like, go back up the graph? And that's where it goes from, is it a directed acyclic graph when you can just traverse it, to, is it an NP hard problem? Or is it like, maybe the way to say it is, I just have to brute force it. I just have to, like, check every way and do that second thing that I was talking about. And it turns out, like, part one is a directed acyclic graph, so we can largely just kind of flow through it. Part two is not, and so we have to check all the ways to do it. And so you want to find an efficient solution to doing it that way. Okay, so that's all the graph theory out of the way. So let's think about then, why is it part one? Well, why is part one directed and acyclic? And it has to do with these slopes. Again, this is one of those things where you just have to visualize the solution to or visualize the graph to be able to see it. I can't zoom in too much while I'm here looking at the graph. You can see the graph is quite large. But I highlighted, when I first printed out, I highlighted the slopes here in green. Hopefully you can see that. And then I highlighted their, like, directionality, like their branching in orange with their number value, right? And if you look at the graph, you can see that anywhere where you could branch, right? Anywhere where you'd think about, if we were back here, anywhere where there's, like, more than one direction, there is always a slope, right? There is always a slope, right? So these slopes are causing directionality. That is to say, if you're going down this direction, you can only go this way and this way. You can't go back up this way. And that's what gives you the, like, quote unquote directed acyclic graph, right? So how do we solve that then? We already know how to do that for part one. Although I just want to make this point salient. You have to look at the graph, right? You have to look at it and say, oh, clearly this is directed, because every time there is a branch, we're able to branch, it is giving you directionality. You can't go backwards in a branch. And so now I know I can solve that in linear time. And what does that mean? Is you're basically just going to try all of the different solutions, right? For part one, right? We know it's directed, we know it's acyclic, and so those are just fancy words of saying, once I hit a branch, I'm only ever going to go out of it. I'm never gonna, I can never, like, go backwards through the branch, right? And that's what these slopes are providing. So when you're reading the problem and you see these slopes, they even illustrate it here in the example. You can clearly see that anywhere where you would branch, there's, like, directionality to it. And that makes solving part one easier, right? What it means is part one does fall into this category. So what does this look like in code? We've seen a lot of this stuff before. I'll go through it just really fast. We have a point that we want to track, right? We're going to do some adding where we're finding neighbors and stuff. So I just impl add for that. And then we want some directions that we can go, right? So I did them separately here because for part one, there's kind of a short circuit that I'll show you. But then I just have a list of directions. And essentially, whenever I'm asking, hey, what is my neighbor of this, which is like this function right here. I guess I can zoom in now that we're not looking at the graph. Whenever I have a neighbor, I know I can just iterate over their directions, which are all 4 of the points, to get me, like, all of their neighbors, right? I'll do the filtering later down below in the map. And so what does the map look like? Well, I'm just going to track all of the points. Again, we're kind of doing a graph. So a hash map that shows the stores the points and their things. We know, and then we can just solve for the neighbors. But we do want to know the start and end, right? And it describes it to you right here, right? As the start is at the top left here, and the bottom is, or the end is down here at the bottom right. So we just need to find those points. And so what does my parse function look like? Again, it's a graph. It didn't feel like we need to use num or anything. I'm just going to iter-enumerate over the lines and iter-enumerate over each character in the line, and that will create a point and, you know, the character in that position. And then to find the start and the end, well, the start is always 1, 0. The test input is like this big, and the real input is like substantially bigger. So I calculated the max x and y, and I knew my endpoint is just the last y and then the last x minus 1, right? That puts me right here, x minus 1. So given that, now I just need to know a neighbors function, right? If I'm going to be traversing this map, I'm interested in who my neighbors are, right? And so that's what this check is for point 1. I can say, hey, give me my current position. And if I happen to be one of these, I know I have to go in that direction, right? It's given me some, again, it's directed, so it's giving me some direction. And so the only place I can go is right. If it's pointing this way, the only place I can go is right. So I just add right to my point and I return that. This is the short circuit I was talking about earlier. And the same is for left, up, and down, right? If I'm going this way, I know I can only go this way. Otherwise, I just need to iterate over all my directions and determine if they're valid, right? And this was kind of a funky way of doing it, but it felt cleaner this way. Basically, instead of like considering all the valid cases, I considered all the invalid cases. And then once I had filtered through all of them, I knew it necessarily would be valid, and so I could just add it. And what does that look like? Obviously, if I'm going right, if I'm going left and encounter a right arrow, I can't go up the slope, so that's not a valid one. Obviously, a hash is not a valid neighbor either, and then you just do the same thing for each of the other directions. So if none of these are the case, right? If none of those are the case, then I know I have a valid neighbor, so I can add that to my neighbors list. So that's the neighbors function for part 1. Again, it's not too tough, but given, you know, the information that you're told about the slopes and how you can go down and how you have to go down the slopes, you can kind of like derive this and derive this from it, right? So that's the idea, is it's just going to give you your neighbors. And then how do you solve part 1 is you just traverse it, right? And see if you can solve it. And again, because it's directed and acyclical, we know we can just traverse, do like a depth first search type thing, or use like a frontier style system. So I am actually implementing them both ways for both part 1 and 2. I won't go over them in too details because we've kind of done these before. This looks very similar to Dijkstra's, right? The key here is we want to track the end, right? We want to track all the ends. Whenever we found an end, we want to keep it. You could potentially keep like a max end value and just update it whenever you see an end. But I just did a list of those. And then once I've done going through, I can literally just pick the max of those and return that, right? And so how do we do the traversal? Obviously, we want to track anything we've seen and not go back. And then we want to keep like work to do on the frontiers, right? So this is the frontier solution, if I didn't mention that. And then what do? We just loop through all of our frontiers. If we found an end, we know we're done, but we want to add that to our list. If we've already been this way, we know we can stop. This turned out not to be a big problem, again, because it was directed, so you kind of only can go one way. But I added it in there just to see, I wasn't sure. But then we just consider all of our neighbors, and for each of our neighbors, we know we're going an additional step, and we add that to our list and we process them. When we're branching, we do need to track the scene, so I don't actually think you need to do this anymore because we know it's directed. If you actually traced this out, again for this, I'll have to shrink it down again, sorry. If you actually trace this out, you can see that it is very directed. And like as you're going down, you're never like coming back to one of these over here, I guess is the way to say it. Like once you've gone down this path, you're not going to end up over here. So you probably don't need to track the scenes. I don't know. I left it in there because at the time I wasn't sure. But anyway, that's the general idea for the frontiers. I did do a depth first search because I think it's actually going to be faster in this case. Again, we have to track all the scenes that we're doing, and depth first leans itself to that. And like the way to think about that is depth first search is going to like what the frontier doing is like a breadth first search, right? Like it's going to put this one and this one on the list, and then it's going to consider this one and this one, and then it's going to consider this one and this one, and it's slowly going down. The way depth first works is it kind of goes bloop. It's going to like consider this one, and then consider this one, and consider this one, and then it's going to work its way back up, and then go to this one, and go to this one, and then work its way back up, and go to this one and this one. And so the reason why this one is a little bit faster is that scene list doesn't have to be like tracked for all of your different breadth values. You can just like update it as you go. And so what does that look like if we're doing a longest find for this via DFS? We still want to track our ins and our scene list, but we just call DFS, and then when we're done, we return our max. The max of the ends, right? And what does that DFX function do? DFS, again, it's recursive, so we want to have some kind of sentinels, right? Some states where we know we're done with like the recursion. And that is, if we're at the end, obviously we're done. If we've seen it before, we're done. Otherwise, we add ourselves to the scene list, consider all of our neighbors, and recursively call it with steps +1. And then once we're done with ourselves, we remove ourselves from the scene list. And so this has, again, the idea of we're adding ourselves to the scene list. So if it was acyclic, we wouldn't do it. I don't think we needed to because it was acyclic. But you kind of do that, and then you're removing yourself. That's important, like in this case, whereas after you've done this graph, when you're coming back up, you remove yourself from A so that when you're going back this way is maybe the thing to think about. When you're going back this way, you've solved it for this way. So you actually do need the scene list. I take that last part back. And it's for these exact cases, like the scene list from here to here it would add this value, but you still want to consider that path when you're going up this way. So that's why we add ourselves to the scene list, and then once we're coming back up the tree, we remove ourselves, is the way to think about it. And that's depth first search is what it's called, right? Is like, this is a breadth first search solution. I guess I could have called it BFS, and this is more of a DFS. I implement them both just so you can look at them in code and see how they work. You'll notice though, like this internal logic is largely the same. You're still doing the same things. One's just in a while loop where you're considering like your frontier, and one is in a recursive solution. And if you look at the answer, the DFS in this case tends to be faster, and so a lot of people will actually use DFSs to solve these. Sometimes it's more easy to think about it in a BFS, but I thought I'd show them to you both this time. Okay, so that's part one. Again, it's directed and acyclic, so you know you can just traverse all the nodes and find them, right? As you're going down, you're whittling down, and so it's pretty easy. How does it change in part two? Well, what it says is, turns out those slopes aren't as slippery, and you can just treat the slopes as normal paths. So they're dots now, right? So how does this change the solution? Whereas once it was very directed, right? Is like when you were at this position, you had to go this way. Now you can actually go back up through it in your traversal, and that makes the path quite longer, right? You can see initially the longest path was 94, but now because you can do it, look at all this traversal you can do. Like I had mentioned before, is right here when you're going down this path. Normally, like consider this point right here. Normally when you've gone down this side of it, the only way you can go is this way, right? But now with part two, you can go up the slope. That's the way to think about it, is now you can go up the slope. So now you can go all through these. And what does that mean? Well, it turns it into it was once a directed acyclic graph to now it's a more general graph, and we know that problem is NP hard. And what does it mean by that? There's just no other way to solve it besides brute forcing it. So as before, I think, yeah, I was kind of drafting this out. So you need to see the X's down here. As before, when I was trying to like think about how to show this, there's no longer arrows, right? So I can go any way in the graph I want. Obviously, I can't backtrack, right? Like if I've already seen A, I can't like go back to A again. Like you can't cause a cycle by just looping forever this way, right? But consider if I add this line right here, when I'm checking the longest path in the directed, right? It's right here. Obviously, I'm only going this way, so I'm only ever getting myself closer, right? But now that I'm not directed, I can go from here to here, and then I can go from here to here, and then from here to here, and then from here to here, right? I'm backtracking back up, not backtracking, but I'm like going this direction in the node. And so it is still acyclic, I guess is the way to say about, is the way to, if I said that wrong earlier, I'm sorry. It's still acyclic, like I can't, there's no cycle in the graph, but it is directed, right? So, or it's undirected, I should say. So I can go back up as long as I'm not backtracking. It's the backtracking that makes it not acyclic, right? Is like, I can't loop in this thing forever because I can't visit a node again. But I can visit a node from a different direction than I could before. And that's what makes the problem, like now it makes it an quote unquote NP hard problem, is I just have to try all the options. I can't just slowly traverse all these paths in the single direction. I now have to consider, given this one, what does it look like if I go this direction? Whereas if I'm here, what does it look like if I go this direction? And you just have to try them all. Okay, so why is that harder on part 2 is, well, you've got a giant graph, right? I'll shrink it down again so you can see it. You've got a huge graph, and so you're going to have to be traversing that huge graph for each of those tests. So the first thing that came to my mind and ended up, or I don't know if it was the first, I actually solved this last night while I had some time. The thing was, if you know the secret about these things and it's a graph thing, it's not actually that hard to solve. You know the longest path. So you have to ask yourself, how do I solve this more efficiently when I'm trying all the paths? I know I have to try all the paths. I don't have a choice because now it is undirected. But I do have to, I do want to do that efficiently. And how do you do that efficiently? Well, if you notice, it's a very large graph, but I actually printed it out here. There's only 36 nodes. And and when I say nodes, what I mean is there's only 32 of these like branches, like right here where you'd branch. And because of that, and there's only 120 edges between those things, right? So you can, as opposed to like literally traversing everything, the way that you could make this more efficient is to like just track the distances between these nodes, right? Like to get from here to here, I know I have to like do all this stuff and it eventually like brings me there. But instead of actually doing that for every iteration, because over 36 nodes and 120 edges, you're going to have to do like, I don't know, 1 million or so checks, maybe even like 10 million checks. Right? We're doing here, there's only 1, 2, 3, 4, 5, 6, 7 nodes and or 7 edges and 5 nodes. But you can imagine all the different checks that you're going to be doing to like solve this. It's like exponentially large to get all of them, right? And so this goes from 30 and 126. Doing all those is like tens of millions of calculations, right? It's millions to tens of millions. The point though is that like that's a lot of work, and so you want to do that as efficiently as possible. And for me, what I said was, okay, well, what if I just track each the distance from each of these, right? So if I'm right here, instead of traversing this thing to get me to here, what if I just track the distance from those two, and then whenever I'm at this node and want to consider going to this one, I know that distance and I don't have to do it. And then if I do that for each node, now consider, like, so for example, this one maybe makes its way over to here, and this one makes its way down here. This direction makes its way up here somewhere. But then, like, this one is connected this way, and this one is connected this way, and this one is, I don't know, connected this way to this way, right? There's all these different connections. Instead of like actually walking the graph, what if I just like, now I can just like, maybe the way to think about it is teleport from one to the other. That will get me there more efficiently, right? And so that's what I did in part 2. The actual solution, I'm still going to do a DFS and a frontier, but I need to do some additional work. And what does that look like? I call this find branching edges function. And all this is going to do is it's going to return me a hash map of those points. It's going to return me the edges is the way to think about it, right? So for each point, how far am I from my neighbors? I'm going to have a list of neighbors and their distance, right? So maybe like, right, if you're at this one, your neighbors is going to be 2 to here, 20 to here, and 11 to here. And that's what this is going to return. So it's just a question of how do I go from like this to doing that? And what does that code look like? Well, first I want to label I want to find the actual nodes. So how do I do that? I label all of the, I label the map with their distances, right? And then how do I know if one of those, or how many neighbors they have, I should say. I label each node with how many neighbors they have. So in the example of right here, this one only has 2 neighbors. In the example of right here, this one has 3 neighbors. In the example of here, this one only has 1 neighbor, right? It can only go one thing. So I figure out all the neighbors, and then I know that the ones that I'm interested in are where the value is not 2, right? If it's 2, it doesn't have any directionality, right? I can only go this way or this way, so it's not a branch. If it's 1, it's got to be my start and end, right? They're the only ones in the graph that only go one direction. And then if it's 3 or 4, I know it's a branch, right? So I'm only interested in the ones that are 1, 3, or 4. And so that's what this does. This will give me all my nodes. And so now I have all the nodes of my graph. All I need to do after that is find the edges between all of those nodes. And how do I do that? Well, I just iterate through all of my nodes. And for each of my nodes, I find my neighbors, right? So I now have like this node right here. And so I want to find all my neighbors. And I just want to traverse those until I hit another node, right? Another branch. And so this one is going to go this way and it's going to calculate that path. This one is going to go down this way to this one and calculate that path. This one is going to go over here and calculate this path, and so on and so forth, right? I'm just going to keep doing that. So you can think about this for loop as going through all the nodes. This for loop is going through each of all the neighbors of that node. And then I just need to track the distance to my next node. And how do I do that? I don't know if this is the most efficient way, but the way to think about it is I'm going to keep finding my neighbors as I'm going down that path. And as long as the neighbors is exactly 1, I know I just have to keep traversing. But once I get to one that's where the neighbor's length is not 1, meaning it's like 2 or 3 or 4, then I know that I've reached the end of the node, right? So, or I've hit another branch is maybe more clearly said. And so at that point, I know I've reached the end, I can break here. Otherwise, I just keep looping until I find that neighbor. So the way to think about it is you're going to start here, and then you're going to go here, 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 here. All these are just 1, right? I can only go forward. And so I do that until I get to here. Now I'm at the branch. And so I know the distance is just all of this space that I've walked. So, and then I just add that to my entry, right? So the distance, right, that I walked, and that neighbor is an edge to my current node. So now when I call these other functions, you can actually see if I go to the main, the two things don't look much different, right? I did one for Frontier and DFS for part 1. I'm going to essentially do the same. I'm still going to do a Frontier check and a DFS check. But these last two, I call it on the branches, right? And why is it on the branches? Because it's still doing the same like logic, but it's doing it on those edges, those edges that we just created, as opposed to the whole map. And that's what adds the efficiency to part 2, right? So as opposed to considering the whole map, I only consider each of those branching nodes and how far it is to each of them. But otherwise, the logic looks largely the same, right? It is the only difference with the Frontier style one, the breadth first search, is that instead of stepping +1 each way, once I get all the edges for the wherever I am, I just add the cost of moving from that, as opposed to just stepping one at a time, right? But the code looks largely the same as before, so I won't go over it in too much detail. It's just the difference is you're still starting at start and you're still looking for ends, but the way that you're getting from start to end is through those edges as opposed to iteratively through the graph, and that adds the efficiency to it. The DFS, again, it doesn't look much different, except now you're considering edges, right? So for my DFS solution, it works the same way. I'm just considering edges for my neighbors, right? So when I'm considering my neighbors, it looks, if you compare the two, they look pretty much the same. It's just now I'm looking at my edges again. So, and that's it. So, and what you end up getting is like this for part 1 and this for part 2. Notice the timing, right? This is the Frontier one and this is the DFS one. You can think about this BFS. This one's notably faster. And again, this one's pretty fast too, notably faster. And that has to do with just tracking which ones are seen, right? You can't backtrack. So we have to track that one. This one's a little bit more expensive to do. This one's cheaper. And so you end up getting to the solution faster. But they're all relatively quick solutions given the problem. Again, I should say given the problem. So just to recap, like what I'm talking about here is when you see a longest path problem, you have to be thinking, what's the secret? Because if they're going to make you traverse the whole thing, it's got to be small. It's got to be efficient, because you just don't have a choice, right? In part 1, it turned out that the thing that made it small and efficient is it was directed. So you're only ever accounting, you're never like having to worry about backtracking. And so you can just you can think about it as just, I'm just walking all the places you could walk, and all of them lead to the end, so I don't have to worry about it. In part 2, that becomes substantially harder, because now you can visit nodes in a direction that you couldn't do it in part 1, making it an undirected graph. So you just have to try all the options. And so you need to look for a more efficient solution. And in that case, for me, what made this a solution efficient was to say, I'm going to take the graph, I'm going to take the large graph and shrink it down into a subset of it, just accounting for the nodes that cause branching and tracking the distances of each of those nodes. If you had tried a brute force without this, when I'm just like, okay, I'm just going to write a neighbors P2 function. You can actually see up here, neighbors P2. I do use it to find the edges or whatever, but or find the nodes for neighbors for P2. But you can see here, it just changes of saying, well, my neighbors are just anything that's not a hash, right? And if you try and solve that, it did not end for me. It was taking like minutes, and so that's why I moved on to trying to find a more efficient solution with the graphs. But again, I just want to highlight the fact of like, sometimes these problems are, do you know the secret? And in this case, the secret was longest path. So you have to ask yourself, is the path directed acyclic? Meaning like I don't have to revisit nodes, or could I visit nodes in like different directions? And if it is, the problem is NP hard. And so you've got to find like an efficient way to calculate that. And that's where you get to the figuring out, the branch, where it branches, tracking distances to those and solving that smaller problem instead of like the whole problem altogether. So there you go. That's my day 2 or part 2 and all of, I guess, day 23. It was a fun one. Like I said, I was able to solve it last night. I think I said that right. I had some time in the evening, and as I was doing it, I was like, oh, I know the secret when you hear the longest path. So it wasn't too hard. And so that's why in this video, I kind of wanted to talk a little bit about the graph theory. Maybe we can go into that in detail a little bit more. And I also wanted to implement it 2 ways. So the solution is longer, but like it was mostly just to show you like there's a breadth first search way to do it and there's a depth first search way to do it. And there's pros and cons of doing both of them. Generally speaking, for this type of problem, DFS is faster. And why is that? It's mostly because you're just updating this list as opposed to making copies of it. You're still in both ways traversing the whole graph. It's just like how you traverse that graph efficiently, I guess is the way to think about it. And DFS in these cases usually tend to be faster. So there you go. That is day 23. I hope you guys have an awesome, and everyone, I hope everyone has an awesome day. And we'll come back again for day 24 and 25. I don't know how that will actually work because I've got holiday stuff that I'm doing. So you might see the solutions come a little later or whatever, but I promise I will get to them, and then we can start doing some other fun programming stuff. And maybe even doing deeper dives into some of these things. So there you go. Talk to y'all later.